Okay, and actually it kind of went somewhat in order. The first three were all horizontal circle ones from last week, so get through those ones real quick since we did ones like them last week. 61, I think, was the first one. Does that sound right? Yeah. All right, in 61, it says a car that is 615 kilograms completes one lap in 14.3 seconds, and one time around the circle is this kind of like, I guess, special time we call time period, big T. That's what 14.3 seconds would be. And the circular racetrack has a radius of 50 meters, so everything's pretty straight up given here. The car does move at constant speed. What is its acceleration as it goes around the track? So the acceleration would be centripetal if it's constant speed, right? It would have to be talking about centripetal because if we're constant speed, we're not speeding up or slowing down, but we are accelerating centripetally due to the change in direction. So based off of our givens, we just got to pick the right formula. We had two possible formulas for centripetal acceleration in our notes. And v squared over r, but since we don't have v, we should consider the other one, 4 pi squared r over t squared. And if we use that form of it, we got all that stuff directly from our givens. So 4 pi squared times 50, all divided by 14.3 squared. Run those numbers real quick. You get about 9.7, 0.65, whatever you round it to is fine there. Meters per second squared since it's acceleration. So, pretty straightforward one. Get the givens out, find the right equations. Don't have to rearrange it, pop them in, go. We okay on that part? Alright, part B. What force must the track exert on the tires to produce this acceleration? So we want to find the force. Well, what force is it talking about? What kind of force? Car on flat turn. What force specifically is the centripetal force? Friction, right. And assuming we're going through it safely, which we should unless told otherwise, we should use static friction. So we remember the formula, centripetal force, Newton's second law, just written for circular motion. Centripetal force equals mass times acceleration, but the centripetal force is the frictional force that it's talking about is for us to find. And we have the acceleration above already figured out, so we just have to use that mass from the givens and plug it in there. 615 times 9.7 or 9.65, whatever you round it to, and you should get somewhere close to what is going on with this? Hold on. I'm in some kind of weird mode I need to get out of. Okay, here we go. 615 times 9.7 gives us a little bit over, or just under 6,000 actually. About 5,965.5. That's a force, so it's in newtons. We expected it would be a fairly big force because this is a force holding a car onto a turn, right? Car that has a fairly big mass. All right on that one? All right, 62 was all the same work. It just wasn't a car this time, and it wasn't friction. It was literally all the same work because the givens were the same. This time it was like a hammer throw. It says an athlete whirls a 7-kilogram hammer 1.8 meters from the axis of rotation, radius. And a horizontal circle is shown in the figure below. The hammer makes one revolution every second. So one time around takes 1 second. That is my time period. What's the centripetal acceleration and what's the tension? So we're again given mr and t, right? So the same work from before. So same equation, 4 pi squared r over t squared. Plug in those numbers, 4 pi squared 1.8 divided by 1 squared. That gets a slightly over 71 meters per second squared. Like 71.1. And for the second part, we okay there? The second part, it says find the tension. That is the centripetal force this time, right? Because it's being whirled there. So we could say the tension equals MAC, and all we got to do is take that mass, 7 kilograms, and multiply it by the 71.1 we just found. And we get just a little bit under 500. About 497.7 newtons would be the tension in that rope. Those are two very similar problems. Let's move on to 64. A rotating rod's 15.3 centimeters long and spun with its axis through one end. So just make sure you read carefully there, because it could have been a variation of this problem that said the axis was through the center of it, but it's at one end. So if this is a rod, if my pen's a rod, the whole thing is the radius, right? Because it's rotating at one end. So that whole 15.3 centimeters is the radius. We want to convert that to meters immediately, though. 0.153 meters. At the other end, it's rotating very fast. We're going to get some big numbers as our answer. The other end of it is rotating at 2,010 meters per second. That would be the equivalent of, just FYI in there, 4,500 miles per hour. So this isn't somebody doing this with it. This is probably some rod on some kind of piece of machinery that's going around very fast for some reason. Crazy fast, probably driven by a motor or something like that. All right. So A, what's the centripetal acceleration? So this one, we just use the other formula that we should know of by now. V squared over R should be pretty simple. But here's where we get real big, because 2010 squared is going to be a real big number divided by that radius, which is a small radius compared to that big number. This is going to get extra big, which is why I'm going to put the answer in scientific notation. If you didn't, that's fine. But once they start getting real big, it's a good idea too. So in scientific notation, rounded to 2 decimal places, you should be somewhere around 2.64 times 10 to the 7th meters per second squared. That's a really big number. But you're going to have, and we noted this when we introduced this stuff, you're going to have if you have a really big speed and a really small radius, you're going to have a crazy high centripetal acceleration, which we do here. And if the centripetal acceleration is really high, then the centripetal force is going to be really high. So it wants to know if we attach a 1 gram object to the end of this rod. Now it doesn't say how we attach it, but more than likely something like glued on or something like that. But we don't know the specific type of force, but we know there's some force holding this 1 kilogram object on that is centripetal, right? And centripetal force is equal to M times AC. It's centripetal because it's making the whatever's attached go in a circle. So we take this mass, which when we convert it to kilograms is 0.001, and take it times this really big acceleration from above. That'll be the force. Since it's a small mass, the force will make the number a little smaller than the acceleration, but it's still a fairly large number for a force. So 2.67 e to the 7th times 0.001. So you would get out about 26400, a little bit over 26,000 newtons. So even if you have this tiny 1 gram object, a 1 gram object is very, very light. I mean, if I put a 1 gram object in your hand and you were looking away and I did it very carefully, you probably wouldn't even know it was there. All right? So, but it still takes a high force if that low mass object is at the end of something spinning crazy fast, right? It still would take a great force to hold it on. We okay on that one? All right, the remaining ones are all of the slightly newer type we did Monday that has something to do with a vertical circle. And as we do the problems, we'll review some stuff within it. So 66 is the next one. Hold on one sec. Oops. I'll just do it below. Okay. A carnival clown rides a motorcycle down a ramp and around a vertical loop. Basically this thing, okay? Just it's a bigger loop and a motorcycle going down through it. And as we noted on Monday, with vertical circles, one thing you got to worry about that you don't have to worry about with horizontal circles is that you're going fast enough to make it through the loop, right? Because if you weren't going fast enough, it's not going to make it. So there's two important positions in vertical circles we define in our notes. We're at the very top and the very bottom, right? So when we're talking about problems that have anything to do about just barely making it through the vertical loop, the top position is what we care about. Because even if I'm going slow at the bottom, I make it through the bottom because the track's underneath me, right? And gravity's forcing me to the track since it's underneath me. But the problem we could have if we're not going fast enough right here is that the track's not underneath me anymore, it's over top, yet gravity's still downward, right? So if I am not going fast enough, that gravity pulls me away from the track, right? So we focus on that top position. And the fact that there wasn't a whole lot given in this problem, but if we do it right, you don't need a whole lot. The only thing it gave us that the radius of this loop in this problem was 18 meters. Again, we're looking at specifically the top position to just make it through. And at that top position, there's two forces on me. Weight, which is always down, right? Or force due to gravity. And what's the centripetal force? What's physically making me go in a circle? With a track? It's not tension, there's no string. What could it be? Yeah. Careful, not friction. Friction would be around a flat turn. What does a track do back on you the whole time? As long as you're in contact with it and really making it around. Yeah. Right, normal, because it's pushing back on you, right? So we define normal, and at the top position, it's pointing down. Now to set up the equation, we got to remember a little note that for the directional aspect of this stuff, to make the math as easy as possible, I put a little side note in our notes before we did any problems that said on Monday that we should try to make the positive direction. Shouldn't try, we should just do it. Make the positive direction towards the center. So even though these two forces are pointing down, I'm going to consider them positive because towards the center is down, isn't it? If I do it any other way, which I could, then you got to make adjustments to your centripetal acceleration signs within the formula, and it becomes more confusing. If you stick to this directional thing with vertical circles, it makes it the simplest as possible. Okay? So both of those are pointing down, but I'm defining down as positive due to the fact that's towards the center of the circle. All right, so those two forces both pointing in the same direction towards the center add together in the left side of Newton's second law. And like always on the right side, we have mass times for a circle centripetal acceleration, right? Now, this problem also gives you a hint. Our goal is to solve for the speed, the minimum speed to make it through, right? I discussed Monday how we do that, but it also gives you a hint in case you forgot. It says at the slowest speed necessary to make it through, the track exerts no force on the motorcycle at the top. Just for a brief moment if we just make it through. So really what it's telling me to do here is make normal force equal to what? Yeah, 0. And again, the thought process of why that's true is because if I barely make it through, you almost, like just momentarily, very briefly, you would actually hang there for a moment until you moved a little bit past the top point where the track got you again. That's when you just barely make it through. Okay? That's why we put that to 0. If it would have been a string problem, we would put tension equals 0 there, whatever it is. But weight still is there, obviously. That's not going to be 0. And at this moment, I'll break weight down into mg. I'll replace that with that there. Equals m, and at this point, I'll replace the centripetal acceleration with v squared over r. The masses cancel, which shows us that we don't need a whole lot of information if we do this right. We just need the radius and to remember the fact that little g is 9.8 on Earth, and that will be v will equal the square root of g times r when we do the algebra correctly. So that will be 9.8 times 18. Run those numbers and we'll get about 13.3 meters per second. So if this motorcycle isn't going at least that, it's not going to work out very good for this clown, right? It's going to fall at some point, unless it's somehow locked to the track, which is probably not. We okay on that one? So that's a good problem, just to remember how we solve for the minimum speed. 67 is really close to that same idea. It more subtly tells you that you're just going to make it through. It's easy to miss, or miss what you have to do, but it's really a similar situation. They give you a diagram in number 67 of a plane going through a vertical loop. But really, the plane isn't the mass in question. The mass in question is actually the pilot, because that's what mass they give you. They don't give you the mass of the whole plane, right? Because the question is about the pilot in the plane. So that pilot's mass is 75 kilograms. And the plane's going through a loop is shown down there. At the top of the loop, when the plane is completely upside down, for an instant, the pilot hangs freely. That's going to be important. We'll come back to that. It hangs freely in the seat and does not push against the seat. The airspeed indicator reads 120 meters per second is how fast we're going at that moment. What's the radius of this loop is what we need to find this time. All right, so what makes the person, I'm not saying the whole plane, okay? What makes the plane go in a loop is still a centripetal force, but it's due to airflow around the wings and their angles of forcing it. But we don't have to think that deeply into it, because it's asking about the pilot, right? What's making the pilot go in a circle directly? The pilot isn't attached to the wings and everything directly, right? He's sitting in the seat. Wouldn't we say that the seat makes him go through the circle? Because the seat pushes back on him centripetally, right? And if the seat is pushing back on him centripetally towards the center at all times, then that's a normal force again, isn't it? A surface pushing back. So that's the first thing we need to realize is the seat pushing back on him makes him directly go through. We're at the top position, just like the problem we did last with the motorcycle. Both of those are pointing like this, right? On him. His weight and the normal force of that seat pushing on him. So we would again have normal force plus weight, plus, because we're still defining towards the center, which again is down, is negative. Equals all that. But back to one thing, this is probably the part of the problem that usually gets people, if anybody struggled at all. I'm going to read a key part one more time. At the top of the loop, when the plane is completely upside down, for an instant, that means briefly, the pilot hangs freely in his seat and does not push against the seat. So that, what it's telling me, and if I really understand this by now, is that he's barely making it through the circle, isn't he? He hangs freely. We said when something just barely makes it through at the top, there's no normal force, is there? If you just barely make it through. So it's really telling us, maybe not real clearly, but it's telling us that we should make normal force 0. Does that make sense? We wouldn't be able to solve this problem if we didn't know that without more information. Because then we'd have a normal force there that I didn't know and don't have anything kind of givens to figure out. But because it's basically telling us we just barely make it through, that's what we do, right? To just barely make it through. So, again, I could turn weight into mg and AC into v squared over r. Although it gave me the pilot's mass, it's not even necessary because it divides out. And I solve for r this time. Multiply it to the left, and at the same time divide by g, and r equals v squared over g. And that's going to be equal to 120 squared divided by 9.8. get a little bit under 1,500. 1,469.4 meters since this radius. Large number, but this is a plane going through a big vertical loop, so it's going to be a large number. We okay on that one? Okay, and finally, the last one, which is the only one that does anything with the bottom of the circle part. Which isn't a big deal as long as we know which way the forces point. We have that in our notes from Monday. All right, we're back to something on a string, though, this time. And we want to just find out the tension in the string as it passes through the bottom position. So the bottom position, no matter what position we're in, we got to remember weight always points directly down. But where does tension point at the bottom position? Because it's the centripetal force. Where would tension point at the bottom position? Down as well or up? Big hint, it's centripetal. It's making you go in a circle. What does centripetal mean again? Towards the center. So if tension is the centripetal force causing the circular motion, the tension's got to be up, right? But I'm still using towards the center as a positive direction. But when I'm in the bottom position, towards the center is up, right? So up positive, down negative. So that makes the formula look very similar to the last couple, just instead of normal force, there's tension. Instead of adding them, they're opposing each other, and we subtract them, right? And that equals, through Newton's second law, MAC. Our givens are the mass of the ball, 1.13 kilograms. The speed that's traveling, 2.4 meters per second, and the radius is 0.5 meters. All the units are good. We now need to just solve for tension. We solve for tension by adding over the weight and then doing some sub-equations. Again, v squared over r for centripetal acceleration and m times little g for weight. Plug in all that, that'll give us our tension. So 1.13 times 2.4 squared divided by 0.5 plus 1.13 times 9.8. Run all those numbers correctly, and we should get something close to 24 newtons. You okay at that one? And remember, there's never a question of a slowest speed to get through the bottom. That's a non-issue at the bottom. So that's pretty much the only thing you would ever be asked in a typical vertical loop problem at the bottom. Your setup equation. All right, so if you're good with all 6 of those and any from last week, just if you didn't get done with those concept builders, make sure you do by the due date set on there. And tomorrow is going to be the quiz. Just a reminder to everybody out there. If you're at home taking it tomorrow, because it's what's tomorrow, Red Day, right? You could have everything open like always. Just make sure you turn it in by the end of the day tomorrow. That's not the end of the school day, the end of the day. Like 11:59 it's set for. Get it in. It's not a real huge test, since this is really just a one section, not a whole chapter. All right, we got a little bit of time left. So in that time, about 15 minutes, I'm just going to go through something a little extra. What I'm going to go over right now, there's not going to be anything like it on the test. This is a unique scenario, okay? So basically, you guys just have to pay attention. You don't have to write it down. You guys that are here, just follow along. I'm going to relate it to, it's actually, I made this problem based off an episode of Mythbusters from a while ago, which we're not going to watch, but we're going to watch a clip of what they're referring to. Let me just switch my thing here. Okay, so anyways, I call this the Batmobile problem, all right? Oh, a while ago, well, it has to be a while ago because Mythbusters hasn't even been on the air for a couple of years, but probably like somewhere around 8 years ago or so, they did an episode on Mythbusters called The Superhero Hour. Anybody happen to see it ever? All right. The purpose of it, well, obviously, if you ever watched any of Mythbusters at all before, the purpose of it is to test something, whether it's possible or not. And almost everything they test in almost every episode is very heavily physics related. And the Superhero Hour one took clips of popular past superhero movies. And they did tests of seeing if they could build things and technology that could do what they saw in the movies. And one of them in that episode dealt with the Batmobile. A clip in one of the older Batman movies, like from the 80s. I'll show you the short clip. I'm going to turn both lights off for you guys that are here because it's a real dark clip. It's hard to see without both lights off. But we'll just watch it. It's very brief and just describe what we're looking for here and what we're trying to prove or disprove. So basically they're in a car chase right now. Right there. I'm going to back that up. One more time. You see a grappling hook. Back a little further. You see what looks like a grappling hook come out and pull it around the turn, right? The car goes very quickly around. So we're going to relate that to... This is going to be a variation, a unique variation of a problem we did. Last week we did problems about cars rounding turns, right? Flat turns. That looked like a flat turn, right? That was a very sharp turn. So some of the numbers I estimated from that video clip what they likely are. All right, and they did the same kind of thing on Mythbusters, and I got some numbers from there. But that's the situation. And let me just read the problem to you and point out a few things. So, searching the internet, found out that in one of the Batman movies, not necessarily that one in particular, that the Batmobile they used in the real movie that they made for the movie was about 4,500 pounds, which is approximately 20,000 newtons. So we know the weight of the Batmobile, okay? We're going to use that as it. We want the Batmobile to take a very sharp flat turn with just a small radius of a 5-meter turn. That didn't look like a very big radius, right? That post at the middle of the turn that the grappling hook grabbed onto was pretty close to the Batmobile. It was a very, very short, tight turn. And it was going pretty fast, right? And that's why it needed the help of the grappling hook. And I estimated probably around 50 miles per hour, which is 22 meters per second, metrically, without slowing down at all to take the turn. Because without the grappling hook, we should remember that what holds us around a turn? Friction, right? Static friction. So we have to assume something here. They obviously fired the grappling hook because he thought he wouldn't make it without it, right? So if we didn't fire it and wouldn't make it, we would start sliding, wouldn't we? If we wouldn't make it. We'd start sliding around the turn and maybe even off it. So in normal problems like this, safely rounding a turn, we use static friction. But if we're going to slide around the turn, we're not going to use static. We're going to use what kind? What's the other kind of friction? Yeah, kinetic. So we have a situation here where friction's still trying and wanting us to help it a little bit around the turn, but we're sliding through the turn with the help of kinetic friction and the tension in the rope. We have two forces that are centripetal, don't we? All right, so that makes this one unique. All right, we're given also that between typical tires and dry road, the coefficient of kinetic friction is about 0.8. It then goes on to tell us, I'm not going to read it word for word, it goes on to tell us that the type of cable that was likely used couldn't have been much more than a 1/2-inch braided steel cable. Because if it was any thicker, you wouldn't be able to shove it in to a small compartment to shoot out. Steel cable is very heavy in itself, and it just wouldn't be feasible if it was any thicker than that. So, looking up what the max tension is by manufacturers of a 1/2-inch braided steel cable, we find that it could withstand 95,000 newtons of tension. So the question is, could this really work if you could physically make a system like this? Could that thing if it clamped on to a post at the center of a turn, could it really help me through a turn going really fast? Would that really be possible? Here's how we're going to figure it out. We're going to solve for the actual tension and compare it to that number. All right? If we get over that, the cord would break, right? And we go flying off the turn. So we'll just, like always, this is the givens in this situation. So the Batmobile weight is 20,000 newtons. And I'm going to need to know the mass as well, so I'm going to very quickly divide that by 9.8 so I have both the weight and the mass. 20,000 divided by 9.8 is 2,040.8 kilograms. The speed which we're told we're trying to round the turn at, which is the equivalent of about 50 miles per hour, is 22 meters per second. And is a very tight, short radius turn of 5 meters. So the max tension, we said that this thing could withstand, is equal to 95,000 newtons. We don't use that number in our solving. We find what the actual tension is and compare it. Okay? We compare that to that number in the end. So again, we set up centripetal forces, total centripetal forces equals MAC. But again, like I described a moment ago, we have tension and kinetic friction, right? Both pointing towards the center of the turn. So we're going to add them together. If we drew a little diagram at any moment around this turn, both of those are helping me around the turn. So when we build that equation, we do tension plus kinetic friction equals MAC. The goal is to solve for tension, so I'm going to subtract kinetic friction to the other side, then I'll start doing some sub-equations. Acceleration based on our givens, because we know V and R, I'll break down to that. If you remember from the past, mu kinetic, or force of kinetic friction equals mu kinetic times the normal force, right? But the normal force, this is a flat turn, right? The normal force is equal to the object's weight, just like always on a flat turn, which was given. So weight is what the normal force is, so I'll sub that in there at the same time. Now I have all the numbers to plug in. The mass of it was 2,040.8. V was 22 squared. R was 5. Mu was 0.8. And the weight was 20,000 newtons. We run all those numbers. Give me a second to do so. I get a tension that would be really huge. And that is way bigger than the 95,000 newtons that cord could hold, right? That cable could hold. So this thing would easily break. It's almost double the tension that it could hold. It would break and snap like nothing, even though it's a strong steel cable. And like I said earlier, if they try to use thicker steel cable, there's really no way you could start coiling it up and get it to shoot out, so that would be unreasonable as well. So, unfortunately, Batmobile is just a trick. It really, that part of it at least wouldn't really possibly work. Now, in the actual Mythbusters episode, they not only ran the numbers, but they took a car, turned it into a Batmobile-looking type vehicle, and they created a grappling hook firing system with a steel cable like this. And first of all, they had a ton of problems just getting the grappling hook when they fire it to actually clamp on to the post they had at the center. So that in its own self is just luck to basically it actually hit and wrap around and not miss. But after a while, they got it to catch. And when it did, And this car they used wasn't probably anywhere near what the actual Batmobile weighed, so it was probably even lighter, and it still made the cable snap like nothing. So they physically experimented and tested it as well, and not even close. It broke off, so it wouldn't be possible. That was just a little something extra since I knew we were going to have a little bit of extra time today. There's not going to be a problem like that one on the test, so don't worry about that. Just figured I'd throw it in there. There's still a few minutes left, but unless there's questions, I'm going to stop there today. You all good? All right.